Hi colleagues, it's Codeberry Club, and today we are going to talk about Neo4j. And today with us Vadim Kovalkov and Evgen Baranovsky. Please don't forget to follow us in Telegram and on YouTube. And let's start our discussion about Neo4j.
Okay, thank you very much for the introduction. Let's get started. So just a couple of words about me. So I'm a lead engineer at EPAM Systems. I have quite a few years of experience with different clouds, serverless, microservices, NoSQL. I've been doing different activities, not just development, but a lot of troubleshooting, some architecture activities, and even a bit of DevOps. Also, I am a certified AWS SA associate, and I like very much to contribute to learning and development activities and doing some architecture research in the background. So with that being said, let's have a look at our today's agenda. First of all, we will have a look at what is SDMX to understand better the intent of the experiment. Then we will go through the objectives and motivation behind my experiment. Then we will consider what tools were used to conduct all the testing. Then we will have at some crucial aspects of the data model used to power up Neo4j. And then we'll have a look at the results of the tests themselves. And finally, we will draw some conclusions as for what is Neo4j good for and probably some cons for against using it. So let's get started. And the first point to discuss is the SDMX standard. SDMX is an open source standard for statistical data exchange, and it includes several artifacts. And the meta model is probably the most important among those artifacts. It includes three key abstractions. So first of all, we have a data set, which consists of a set of measures. And those measures are uniquely identified by coordinates called dimensions. And finally, we have some attributes, which are just non-unique properties for different metadata purposes. Let's have a look at an example of how a typical SDMX dataset may look like. And let me note that most of the time, SDMX data is organized into time series. And we see exactly this case on this slide. So in this case, we separately consider the time dimension and use the remaining dimensions to identify the series itself. So in this case, these are some financial indicators captured for certain countries for certain period of times. And then we have a roll-up of time points, which capture the measurements themselves. And the meta model for this data set looks like this. So we have just one measure. By the way, we can have multiple of them, which is pretty useful for modeling such things as questionnaires, for example. Then we have 6 dimensions. One of them is time period, as I mentioned already. And then we have a set of non-unique attributes, which are used as some sort of metadata. So for example, a comment or the clarification on what units were used to capture the measurements. And in case you would like to dive deeper into the topic, you may follow the links presented on this slide. So now we understand what is SDMX, and it's time to talk about the experiment itself. First of all, I had some motivation behind doing all that stuff. The reason for this experiment was to find out an optimized solution for my current production project, which has some non-trivial requirements, let's say it this way. So first of all, we deal with a mixture of OLTP and OLAP load. Then we have to make all our data bitemporal. So this means that we need to capture not just some logical time periods, but also the timestamps at which each time point were changed physically. So for example, some mistake correction. Then we have to support data lineage for such tasks as audit. And finally, the data sets we deal with are not very big, but not very small. So they are measured in tens of gigabytes usually. And the current solution that we use in production is a combination of Postgre and Elasticsearch, which obviously entails some data denormalization, complications to transaction management, because we have to coordinate two disparate systems, and the design actually looks very similar to two-phase commit. And finally, we have some complications with operational activities, troubleshooting, and monitoring the system. So my question was whether it's possible to find a technology which would cover all our essential requirements in one shot. And I decided to consider Neo4j graph database because it's very friendly to such features as data lineage, because it's a GraphDB, by the way. It's quite a mature product with good support and huge community. It supports several query languages, Cypher among them, and it has some advanced features like transactions and clustering. Plus, SDMX itself may benefit from the capabilities of graph databases for capturing some advanced hierarchies, because we may work not just with series and observations, but also with some higher level structures like dimension groups. Okay, so these were my objectives and motivation, and now let's talk about the toolkit I used. So the toolkit included Neo4j desktop, which is a bundle of some sort of IDE for Cypher language, plus a free enterprise license for Neo4j itself, which is quite convenient. Then I used old good JMeter for perf tests themselves, and I used the ELK stack to monitor hardware usage. And finally, I had to write some custom Java code, of course, to generate the test data itself. So this slide presents a screenshot from Neo4j desktop, and it shows that we have some nice syntax highlighting in the upper part, and we have a visualization of the query results at the bottom. Also, we have some metadata panels and the ability to display such details as, for example, query plan explanation, which is quite useful for optimization and troubleshooting. And if to talk about hardware monitoring, I had to use two setups, different setups for the case when I tested Postgre and Elasticsearch, and another one for testing Neo4j. That's because I used Docker to run Postgre and Elasticsearch, but Neo4j desktop imposes that I have a real top-level process with Neo4j. And for the combination of Postgre and Elasticsearch, I had to use some nasty solution based on PowerShell script, which pulled the Docker stats command, which then was dumped into a log file. And that log file was fed to FileBit, which is one of the bits. And bits are lightweight alternative to Logstash in the ELK stack. And FileBit just was responsible for indexing the log file data and sending it to Elasticsearch so that it can be later visualized using Kibana. And you may ask that why is this so complicated? Well, of course, I could use Dogbit, which would replace these ad hoc solution based on PowerShell script, but unfortunately, this thing refused to work on my Windows machine. And the second setup for Neo4j looks like this. It's a lot simpler, so I have to use just Logstash, which uses a JMX plugin to collect statistics from Neo4j directly because Neo4j runs in a Java virtual machine. And the data goes directly to Elasticsearch without any additional transformations. Now let's talk a bit about the data model and complications related to modeling data for SDMX. The first time approach was quite straightforward. So I created nodes for every major abstraction in SDMX. And first of all, I had to model series. So each series is represented as a unique node, which is identified by its dimensions. And we have a separate snapshot of attributes. So remember that we have to deal with history tracking and data lineage. And for this reason, we capture timestamps, which designate from which time point and to which time point every snapshot is valid for. Then we have one snapshot node per observation, 3 nodes in this case. And on top of that, we can have the aforementioned dimension groups as separate nodes as well. But I didn't use them in testing, so this slide just shows that this is possible. And a sample Cypher query for fetching data from this model looks like this. So first of all, we find all series that match certain filters. In this case, we request data by one country and one sub-indicator. And then we sort it by dimensions, take the first 2 series. Then we traverse the relationships from the series towards their series snapshots, which is about attributes. And finally, we collect all the observations connected to the series found. And of course, in every traversal scenario, we use timestamp-based filtering to retrieve the latest data in case we have some history accumulated over time. And that was not enough, unfortunately, because when I tried to test more complicated queries, and to be more precise, aggregation queries, which in SDMX look like facets, let's say it this way. And here I found out that Neo4j is not able to provide good performance in real time for aggregations, so I decided to introduce some pre-calculated aggregates. Sorry. And I had to introduce an aggregate on the level of series to pre-calculate the time period ranges contained inside the series, and also a separate dataset level aggregate, which aggregated different unique dimension values, and also time period ranges as well. And an aggregation query looked pretty simple in this case with aggregates. So we begin with finding all the series that we need, again by one specific country. Then we collect their aggregates. And finally, we build a response in an appropriate form. Okay, and the next challenge which I had to face to prepare test data was about transactions. So why did I have to do some fine-tuning here? That's because, first of all, Neo4j keeps all its native transactions in memory. So this obviously means that we are able to process quite limited transactions at a time. And on top of that, it provides just read-committed isolation out of box. So in case we need to provide some more complicated semantics, we need to write some code. And let's have a look at the transactional model that I came up with. The first step is to introduce a metadata node for tracking transaction state, which includes some unique identifiers, status, and timestamps. Then, on the first step, we use a custom stored procedure. And by the way, Neo4j has a great API to write plugins for it, including stored procedures. And we use such a procedure to perform some sort of CAS operation. So we atomically acquire a lock on the series node and try to attach the transaction ID to it. And in case there is already some transaction sitting on this series, we retry for several times and then fail in case we don't manage to overtake that ID. The next step, in case the locking step succeeds, is to do the manipulations themselves. So in this case, this diagram shows how to delete an observation from a series. So because we have to track history, we have to adjust some historical relationships, not just drop data. So we take the existing relationship and mark it for modification. Then we add a new snapshot of that relationship with updated timestamps to indicate that this observation snapshot is no longer valid for eternity. It's valid just up to the transaction time. Then we have to update the series aggregate as well. And here we need to do similar modifications to adjust the relationships. And finally, we create a new snapshot of the aggregate. On the final step, when we need to decide to commit or roll back, we just update the status of transaction, and read queries are able to pick up changes just immediately. But before this, we of course need to update the dataset level aggregate to reflect the recent changes and to mark the previous dataset aggregate to be valid to just the time when the transaction started. So these examples showed just the basic ideas behind this model, and let's go quickly through some details without showing too many pictures. So first of all, how do we roll back in case we need to do this? We simply use a different status value for transaction. Instead of commit, we specify rollback. In case we need to add an observation instead of deleting it as just shown, we create a new node with observation snapshot and add a new relationship to it. Pretty straightforward. In case we need to update an observation, so this is probably the most complicated case. In this case, we need to create a new observation snapshot node connected to the existing series node and then update timestamps for the relationship which points to the already existing observation snapshot. And finally, as you probably observed, we may get some trash data in case some transactions roll back and leave some pending nodes which are not visible to our read queries. So in this case, we may use some background process which periodically checks for rolled back transactions and cleans up all the data associated with them. So now the most interesting time to look at the perf test setup and results. So first of all, about the hardware that I used. So I used a standard EPAM laptop with a 4-core hyper-threaded CPU, 32 gigabytes of memory, and an SSD. As for software, that's pretty standard. I used Windows 10, Docker for desktop, pretty old one, because for some reason I faced some memory leaks on newer versions. So probably need to check a little bit later for new patches. And Neo4j desktop 1.5.8 and JMeter 5.5. As for the dataset size, I generated a data set which included 100 countries, 100 indicators, 10 sub-indicators, 200 time periods. On top of that, I added some attributes, and that totaled it out in 100,000 series and 20 million observations. Pretty big chunk of data, actually. And as for the test scenarios themselves, first of all, obviously, I had to ingest data to Neo4j and Postgre and Elastic. I used one-threaded ingester for this case. As for read query workload, I used 1,000 iterations per scenario, and the scenarios included retrieval of data with pagination and no filters, with low selectivity filters, high selectivity filters, and a couple of data availability requests, which are those aggregation requests that I've talked already about. Okay, so let's have a look at some results. Unfortunately, on ingestion, Postgre and Elasticsearch obviously took the lead with pretty huge difference, but this is not surprising a lot because graph databases are typically not the most fast for writing data. Then, if to have a look at the hardware stats, Postgre and Elasticsearch consumed pretty humble amount of resources, but only except for a short spike at the end when we had to commit a transaction and index some data in Elasticsearch. But as for the memory, the consumption was pretty steady. Now let's have a look at Neo4j. So Neo4j is a bit more hungry by default, and this is not surprising according to documentation. So Neo4j unfortunately has quite a high entry point for hardware, but overall it was pretty reasonable on such a humble machine and pretty stable overall. No big spikes. Then as for read test results, the situation changed. And Neo4j took a lead with a leap of 2x or even 3x increase in performance. And this is even more obvious for the data availability requests, thanks to the pre-calculated aggregates that I created for the data model. Okay, and as for the hardware, here we have a pretty humble picture for Postgre and Elasticsearch. They consumed even less resources for the read workload, which is pretty natural. And Neo4j was also less hardware consuming, but more hungry than Postgre and Elasticsearch. But overall, again, within limits of reasonable. And what conclusions can we draw from this? So first of all, about pros. Neo4j is incredibly flexible and extensible because it's possible to write plugins for it, and it provides a pretty good API for that. Then it provides a decent read performance and quite friendly to complicated data models, which support such features as lineage, bitemporality, and similar stuff. As for cons, Obviously, Neo4j is quite hungry for hardware, especially main memory, because it keeps a lot of data in memory, including transactions. And also it may be quite slow on writes, but it depends on the workload, so be careful with this. And finally, as for license, there might be an issue as well. So the license is free only for educational and research purposes, but not for commercial use. In case you would like to use enterprise features, which include clustering and some decent optimizations to the internal engine, you need to buy a subscription. And also, I would like to mention a couple of words about what could be improved about my experiment itself. So obviously, I spent a limited time on this and it was imperfect, but I have some ideas how the situation might be improved. So first of all, it might be worth to take a deeper look at configuration of Neo4j. I tuned just basic parameters and didn't touch on such details as I/O limits and transaction logging. Also, it's worth to take a look at how my custom stored procedures work, and probably have some profiling data on them. Probably I have some bottlenecks there. Then I used just a fixed amount of series ingested per batch. 400, probably smaller batches would perform better. So I just needed more time to try different values. And of course, there are some ideas about the model itself. So first of all, it's quite possible to minimize the use of user procedures and leave only such things as CAS operations and locking there. Then it might worth to try minimize mutation of data and use append-only approach mostly, because the logic for building diffs is quite complicated and might have an effect on performance. The same goes for duplicates. Also, it could be possible to develop a lighter version of ingestion algorithm for the case when we deal with an empty data set and ingest data to it from scratch. So in this case, we don't need to perform diff logic again. And finally, not all the cases are even, and probably sometimes it makes sense to disable such features as history tracking. For example, in case someone wants to experiment with data in a sandbox environment, which is quite different from production, where we need to deal with such things as audit, security, etc. So this is it about the information that I would like to convey today, and it's time to engage into conversation. So I pass the word to Vadim and Andrei. Thank you.
So first of all, I'm going to say that big thank you for the talk, and I'm going to ask our listeners, feel free to put your questions in our chat, and we will ask the questions. So, Vadim, do you have any questions?
Actually, I have the only one question. Did you bring this idea and the results of this performance investigation to your customer? Did you show the metrics, and are you ready to discuss with him or her how it could help you?
So basically, I must tell that we have already had some experiments with alternative data storage implementations. In particular, we have already tried to use a columnar storage with our architects on the project. But as for my Neo4j experiment, unfortunately, I haven't had a chance to present the results because I would like to probably try some additional fine-tunings that I've mentioned on the last slide over here.
Okay.
Before I can come to with some good proposal.
So, and could you compare your experiment with the columnar databases and your one with the Neo4j graph database results?
Yes, so I can provide some details here. First of all, as for the concrete technology, we used Microsoft SQL Server columnar index, clustered columnar index, and it showed similar performance on the right. So it consumed a data set of comparable size of 20 to 30 millions of observations within about 30 minutes on the same machine. And for the read performance, actually, it would fall even worse than Postgre and Elasticsearch in this case. So it looked not that good, actually, because it's created mainly for analytical workload. But as I've mentioned, we have a mixture of transactional and analytical load. So it would be more concise to try some hybrid databases in this sense.
So actually, I think that you was following and was trying to save some money to just decrease the costs of current architecture. And
well, it's of course it would be nice to have some cost reductions, but from the licensing options of Neo4j and its requirements for hardware, it's obvious that Neo4j is not the cheapest solution here, to be honest.
Actually, if we could compare some resource consumption and the license price, it could be time to time or decision by decision. It could bring some benefits, but we need to compare it.
Yeah, but it's necessary to compare the actual numbers because Elasticsearch, of course, is not cheap as well. For example.
Yeah, I get it. I get it. Thank you, Andrew. Take a mic. Seems like we lost Andrew, but I believe that he will be soon back, and we can try to discuss this topic and discover the topic a bit more. So, what kind of most tricky situation you faced during the diving deeper in the Neo4j implementation and the migration?
So first of all, I was quite surprised with how interesting its default settings are. So for example, it turns quite an expensive option for keeping transaction logs. It limits itself by the number of days. So this resulted in tens of gigabytes of data in my case. So I had to change its lifecycle policy settings to limit by the size of logs, not by their recency, let's say it this way. And obviously the next biggest challenge was to deal with custom transaction management because I had to write a lot of concurrent oriented code, deal with logs, etc. So probably these two aspects, first of all.
Okay. Thank you. Oh, who is back? Andre? We didn't notice that you've been lost, so you're welcome.
Hello.
Hello. Take the mic.
So I have a question related to scalability of the solution based on Neo4j. If we have a really huge database with a lot of connection between nodes, how to scale it?
So in terms of clustering and scaling, Neo4j natively supports replication. which is not very beneficial in case we have to deal with huge data. But it's possible, for example, to implement manual partitioning, because we can create separate so-called data graphs for different data sets and map them onto different nodes in the cluster.
Do you have any comparison with Postgres or MySQL databases? How hard to scale? How?
Well, to be honest, if to take, for example, my current production project, we've just entered the phase when we deal with the requirements of high availability, and we've just started with scaling. So it's an open question. And probably the biggest question here is about Elasticsearch, because we use it in quite an unconventional way. We have thousands of small indexes, which is not very good for it, to be honest. And in case we need to scale, it might be even more interesting, because one of the main bottlenecks for us now is the overhead of managing cluster data on the master node. So it has to spend a lot of memory onto keeping the shard mappings and node memberships. So in case we grow our cluster even bigger, the master might die even faster. So this is an open question, actually.
Okay, and we have a question in our chat. What do you think is the best application for Neo4j that makes it worth the hassle? Which cases is absolutely shines in?
So obviously, Neo4j will shine in such situations when we have to deal with some social networks, because graph databases basically emerged from the necessity to manage highly connected data in such applications. Then, of course, we might use basically any graph database, including Neo4j, for such things as infrastructure topology management, when we need to model complex network topologies and plan outage maintenance. Then we can use graph databases for fraud detection. It's quite widely used in fraud detection algorithms in financial domain. And we can also use graph databases quite efficiently for such tasks as master data management, which is about data lineage, which I've already mentioned in my experiment.
Okay, thank you. Thank you for the answer. Uh, so, I have probably last one question from my side for today. As I understand, you manage your Neo4j cluster manually in your teams. Do you know about any services based on popular cloud platforms like Neo4j in AWS, in Azure, or in Google Cloud, or is it available or not?
Yes, it's available. Unfortunately, I didn't recall the exact name of this technology, but Neo4j provides a completely managed product, and it's able to deploy, I believe, in all major clouds, including AWS and Azure. And as well, it has a custom deployment options for fine-tuned for such tasks as machine learning, even, which includes pre-built libraries which augment its native capabilities of computing. So there are options in the cloud.
So thank you, Vadim. Do you have any questions?
No, actually.
So I think that's it for today. Thank you for the talk. Thank you everybody who was a listener, who asked the questions. Don't forget to follow us on YouTube and in Telegram. And see you next time.
See ya. Bye.
Thanks for your attention. Bye.
Bye bye.